We're going to take a quick break from matrices for 1 unit. Don't forget everything we've talked about because they're going to come back next unit. Last unit we talked about matrices. This unit we're going to talk about probability. And then those two are going to come together in our final unit using matrices to model probability situations. So don't forget what we talked about as we step away for a bit to talk a little bit about probability. And before we can dive too much into probability, first we need to know how to count. So today what we're going to look at is how we can solve some basic counting problems. Now, by counting, I don't mean counting 7 items and finding out how many there are. I mean counting hundreds and hundreds of items in a matter of a few seconds. We're able to do that with some counting tricks that we're going to talk about today. But first, we're going to start off with setting this idea of a set. A set is a collection of objects called elements. And I'm going to underline set. That's a vocabulary word we're going to be using, and underline elements. That's another vocabulary word I'm going to be using. A little bit of vocabulary around these sets and how to talk about it. First, before we get into the vocabulary, an example of a set, we often use these squiggly brackets and then list the elements of the set. Maybe the elements of the set are the even numbers through 10. 2, 4, 6, 8, 10. That is a set of the even numbers. They don't have to necessarily be numbers or even variables. They could be colors. Maybe the set is red, blue, green. That is a set of colors. The elements are colors. And a set doesn't even have to have anything in it. We have this thing called the empty set. Another vocabulary word, and that is a set with no elements in it. Often when we're talking about the empty set, we'll represent it with a circle with a slash through it. That symbol represents the empty set. There's nothing in this set. We also have this thing called a subset. A subset is a set where every element of the subset is also a member of a larger set. And notationally, let's say A is equal to the set red, blue, green, and B is equal to the set red, blue. You notice every element in B is also a member of the larger set A, so we could say B is a subset of A, and this notationally, it's a sideways U with a line under it. This notationally means subset. B is a subset of A because everything that's in B is also a member of the larger set A. That is a subset. Another type of problem that could be considered is if I have the set 1, 2, 3, I could list its subsets. Subsets would include the single items 1, 2, 3, subsets that have 2 items in them 1, 2, 2, 3, or even 1, 3. Also, the empty set would be considered a subset because every element in the empty set is also in the bigger set. There's nothing in the smaller set, and those are all accounted for. Also, the entire set 1, 2, 3 is considered a subset as well, because every element in there is a member of the other set 1, 2, 3. Another concept that we might be interested in looking at is this concept of union. We can find the union of two sets. When we do that, we are asking for all elements in either set, or both. So for example, if A is equal to the set 1, 2, 3, and B is equal to the set 2, 3, 4, we could find A union B with this symbol meaning union. It looks like a capital U, probably more like a horseshoe in that it's really skinny. Would be all the elements in either set A or set B or both, and we see 1, 2, 3, 4 in those sets. Often union is associated with the word or. Is it in set A or set B? Union is the word or. The other operation used a lot is intersection of two sets. And the intersection is a list of the elements in both sets. This is where they overlap. You might think of the word and here. It's in set A and set B. So for example, if one set, I'll call it set A, is 1, 4, 5, and set B is 2, 3, 4, 5, we might try and find A intersect B with this symbol. It looks like an upside down U, meaning the intersect would be all the elements that show up in both. You'll see the number 4 shows up in both, and the number 5 shows up in both. Because it shows up in both, A intersect B is 4 and 5. Some more vocabulary to set this up. We haven't even gotten to the math part yet. We have this thing called the universal set. Often we'll use U to represent the universal set. And this is the list of all elements under consideration. So if we say the counting numbers, the universal set would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so forth. This mainly sets up the idea of the complement. The complement is the elements in the universal set but not in the given set. So let's say, just for the sake of conversation, the universal set we're working with is the numbers 1 through 5. 1, 2, 3, 4, 5. And another set A is equal to 2, 4. We might be asked to find a complement, or a complement. Now these two symbols here mean complement. And depending on the textbook, you'll see one or the other, or sometimes both. The bar over the A, or looks like a pitchfork, it's actually a Greek letter. That means a complement. I will use the bar more often in class and on the test. I won't use the other one at all. I use the bar almost exclusively. So a complement are the things that are in the universal set but not in A. And you notice 1 is missing, 3 is missing, and 5 is missing from the list in A. So therefore a complement is 1, 3, 5. That is a complement. The complement and the set are considered disjoint sets. There's lots of disjoint sets that don't include complements, but complements are one type of disjoint sets. A disjoint set are two sets that have no elements in common. In other words, if we took set A and found the intersection with set B, we would get the empty set because there's nothing in common with both A and B. So all this notational stuff, let me give you a brief example of what you might be asked to find. I'm just going to do one of these. Let's say the universal set for this example is equal to the numbers 1 through 7. 1, 2, 3, 4, 5, 6, 7. And the set A is equal to 1, 3, 5. The set B is equal to 1, 4. And the set C is equal to 2, 4, 6. And we are going to find A union B complement intersection C complement. Well, to do this, we kind of have to play with the parts. The parts that are combined, you'll see first there's this A union B. So first let's find out what A union B is. A union B is the list of all elements in A or B. That would be 1, 3, 4, and 5. That's the list of anything that shows up in A or B. But we're asked to find A union B complement. That would be the things that are not listed in this set. Okay? Complement. Going to the universal set, what is missing in the universal set? Well, we've got 1, but 2 is missing. We've got 3, 4, and 5, but 6 and 7 were missing. Then you'll notice on the right side, we're going to intersect that with C complement. So we need to know what C complement is. And that's what C is missing that's in the universal set. C has 2, 4, and 6. It's missing 1, 3, 5, and 7. So when we find the intersection of both of these together, kind of see how we start in the middle and grow out, the intersection of A union B complement intersected with C complement is where these two sets overlap. What do they have in common? Well, you'll notice the only thing they have in common is 7. So therefore, the complement of A union B intersected with the complement of C is just the element 7. Your assignment today takes a look at some set notation, manipulating complements and intersections and unions, and making sure you know how to interpret that notation. So when that vocabulary and stuff comes up throughout probability, you'll know what we're talking about. Something that helps us with counting. Now that we've got sets, we're often interested in the number of elements in each set or in each group. Something that helps us with the counting are these things called Venn diagrams. A Venn diagram visually shows sets as overlapping circles. So for example, we might have this circle overlapping with this circle, and we're going to have a rectangle around it. Inside this rectangle we're saying is everything. It's the universal set. And let's say we do a survey to see who prefers McDonald's and Burger King. So one circle represents McDonald's, one circle represents Burger King, and they overlap. We find out in our survey that 12 people prefer McDonald's, 15 people prefer Burger King, 7 people like both, and there are 6 that didn't like either. Visually, we can see really quick now from this that the survey has 12 plus 7 plus 15 plus 6. This was a survey of 40 people. We can see visually that 12 prefer McDonald's only, 15 prefer Burger King only, 7 prefer both, and 6 prefer neither. We could even go a step farther and say of those who prefer McDonald's, 12 preferred McDonald's exclusively, 7 preferred both. That means a total of 19 like McDonald's. Some of those 19 like both, but 19 like McDonald's. We also see 7 plus 15, 22 like Burger King. And so we can kind of pick the spots and really visually see who likes what. Now actually, when we're working with Venn diagrams, we do this actually in much the opposite of what we just did. What we just did was we took the Venn diagram and kind of interpret it. Normally what we do is we have information about a group of people that to help us organize and understand what's happening, we make a Venn diagram to see how the groups are split up. So let's say in a survey of 50 people, "31 watch CNN, 28 watch Fox, and 18 watch both." We're interested in the question of how many watch neither. So let's set up a Venn diagram to represent this. We'll do one circle to represent CNN. We'll do another circle that overlaps to represent Fox. And then we'll put the universal set around that includes everybody. Now the problem with the 31 watching CNN and the 28 watching Fox is that it includes the people who watch both in both groups. So what's going to help us is to start in the center of the Venn diagram and work our way out to the outside. We see first that 18 watch both. So I'm going to put that in my diagram here. we've got 18 people overlapping watching both. There's a total of 31 who watch CNN. So in the CNN bubble, there needs to be 31 people, but we've already accounted for 18 in the center. So if we subtract out the 18, we get 13. That means there are 13 people over here that are just watching CNN. Similarly with Fox, we have 28 people watching Fox. Well, that 28 people includes the 18 that are watching both. So we're going to subtract the 18 off to see how many just watch Fox. When we subtract, we get 10 people just watching Fox. But we're told the survey has 50 people total. There's 50 people total. We've got 13 just watching CNN, 10 just watching Fox, and 18 watching both. Those are all accounted for, so we'll subtract them out. Subtract 13, subtract 18, subtract 10. And if we do that on our calculator, 50 minus 13 minus 18 minus 10 is 9. There are 9 on the outside. To answer the question, how many watch neither? 9 people at the survey watch neither CNN or Fox. Venn diagrams can get quite complex and involved as they grow. If we have time in class, we'll do a really fun one. But for now, in this lecture and discussion, we're going to stop at 3 categories. That's what this next example is. In a survey of 100 people, 42 enjoy romance novels, 36 enjoy mysteries, and 41 enjoy nonfiction. We also know that 20 enjoy romance and mystery. 15 enjoy romance and nonfiction. "14 enjoy mystery and nonfiction." And of everybody, 5 enjoy all 3. How many enjoy none? So here we have 3 categories going on. We've got one category, one circle that's going to represent romance novels. We've got another category that overlaps. That's going to be our mysteries. And then we've got a third category this time that has to overlap both circles. And this third category is going to be our science fiction. And we'll put all of these in the box of the universal set, which includes some outsiders. Again, the philosophy, though, is going to be exactly the same that we saw in the previous problem. We're going to start in the center, and we are going to work our way out of the center. In the very center, overlapping all 3 circles, we see 5 people that enjoyed all 3. Now what we'll do is we'll take a look at the people who enjoyed groups of 2. Maybe we'll do this group of 2 over here on the left. That's inside the orange circle and the blue circle. Notice we've got, I'll even outline it, orange and blue overlapping right here. That is romance and science fiction. How many enjoyed romance and science fiction? Romance and science fiction. I'm sorry, it's not science fiction, it's nonfiction, isn't it? Nonfiction. That's why I couldn't find it. Romance and nonfiction. That's 15. Let's get the number in the circle. 15 enjoyed romance and nonfiction, but we don't want to double count the 5 in the center, so we'll subtract out the 5 in the center, giving us 10 people in the romance and nonfiction category. Let's look at another overlapping group. Maybe this group right here. Notice that overlaps the green and the blue circle. That's the romance and mystery group. Romance and mystery. That would be these 20 people who enjoy romance and mystery. There's 20 of them, but we don't want to double count the 5 in the center, so we'll subtract those out, giving us 15 enjoying romance and mystery. You can see then our next overlap is between the green and the orange. That's the mystery and the nonfiction. And that gives us 14. Just do little arrows. I'm running out of different symbols. 14 enjoy mystery and nonfiction. But again, we don't want to double count the 5 in the center, so we subtract those out, and we get 9 in that space. Now we're ready to continue moving out in the circle. The next, we're going to look at the exclusive groups. Let's look at the romance group right here. Romance should be blue here. How many enjoyed romance? It says 42 enjoyed the romance novels. But you'll notice inside the blue circle we've got 3 numbers. We have to subtract out the 15, subtract out the 5, and subtract out the 10. Because we don't want to double count those groups. So we're subtracting out 15, 5, and 10. That's 30. So there's 12 that were exclusive romance nuts. Similarly, when we go to the green circle, green is the mystery exclusive group. There's 36 exclusive mystery people. We need to subtract out the overlaps, though. Subtract out the 15, subtract out the 5, and subtract out the 9 also. And you might need a calculator for that. So we've got 36 minus 15 minus 5 minus 9 is 7. So we have 7 mystery exclusive groups. Then we go to the orange circle, the nonfiction exclusively. 41 in that group. We'll subtract out the overlaps in the orange circle, which is 10, 5, and 9. So we've got 41 minus 10 minus 5 minus 9. That leaves 17. There are 17 in this group. Question wants to know how many enjoy none of these categories, and that's that universal set. We are told the survey originally had 100 people. So if we start with the 100 people, we can subtract out each of the numbers that are represented in our circles. In no particular order, almost just reading left to right, we get to subtract out the 12, subtract out the 15, subtract out the 7, subtract out the 10, subtract out the 5, subtract out the 9, subtract out the 17, and that tells us how many fell into none of these categories. So 100 minus 12 minus 15 minus 7 minus 10 minus 5 minus 9, minus 17. I'm getting 25. So we have 25 left over to finish the universal set. 25 outside. How many enjoy all three? 25. I'm sorry. How many enjoy none of these? 25 enjoy none of these categories. And so that's kind of the idea behind these Venn diagrams. We draw overlapping circles and kind of work from the inside out to determine how many are in each group. I want to hit one other type of counting that you're going to see on the assignment today, and then we'll get into the real fun counting tomorrow. But today we're going to take a look at this thing called the multiplication axiom. And to set up the multiplication axiom, instead of just straight defining it, I want to first look at an example. Let's say a pizza can have one of 3 toppings. Maybe we'll say pepperoni, cheese, or mushrooms. And one of 2 cheeses. I'll just say white and yellow cheese. You can figure out what kind of yellow cheese you like, or white cheese you like. But just for the sake of this conversation, what we really have is a couple choices along the way. The first choice is in topping. You need to choose if you want a pepperoni topping, Canadian bacon topping, or a mushroom topping. And then once you've made that choice, you need to choose one of 2 cheeses. You can choose a white cheese or a yellow cheese, and that doesn't matter which type of topping you got. So on the Canadian bacon, white or yellow. On the mushroom, we could choose white or yellow cheese. Notice that gives us several different types of pizzas. We can have pepperoni with white, pepperoni with yellow. We can have Canadian bacon with white or Canadian bacon with yellow. We can have mushrooms with white, or we can have mushrooms with yellow. What we're interested today is the fact that total there were actually 6 choices for pizzas that we could use. Now what's interesting about this is if I had started by saying choice number 1, topping, there were 3 choices for topping, and choice number 2, cheese, there were 2 choices for cheese, it ended up giving us 6 choices. Well, you can see if I just knew the toppings were 3 and the cheeses were 2, I could have gotten my answer, my solution, by multiplying these 2 values together. 3 times 2 is 6. This is what the multiplication axiom says. The multiplication axiom says that if we multiply the number of options for each choice, we get the total number of choices. So for example, let's say we've got a man who has 2 pairs of shoes. Three pairs of pants, and 4 shirts to choose from. We can determine how many total outfits he could come up with for the day by looking at each individual choice. The first choice is the shoe. The second choice is the pants. Probably need more letters for shoe because the third choice is shirt. So for the shoe, there are 2 choices. For the pants, there are 3 choices. And for the shirts, there are 4 choices. To find the total number of outfits, we just have to multiply the choices together. 2 times 3 is 6. 6 times 4 is 24 different outfits that this man could select for the day. His wife only hopes that they match. How about this problem? Let's say a license plate has 2 letters followed by 3 numbers. And they have a rule that the last number must be odd. How many different license plates could we create that satisfy these requirements? Well, we've got 2 letters followed by 3 numbers, so 5 blanks total. How many letters can we choose for the first? There's 26 letters. The second letter, 26 letters. And then we've got 3 numbers. There are 10 unique numbers. Don't forget about the number 0. And 10 unique numbers for the second spot. However, the final character of the license plate must be odd. And there are only 5 odd numbers. To find out the total number of license plates, we just have to multiply these together. 26 times 26 times 10 times 10 times 5 gives us 338,000, 338,000 different license plates that satisfy these requirements. Here's another version of the same problem. How many ways can 5 people sit in a row? Well, 5 people, there's 1, 2, 3, 4, 5 people. The first person to sit down, the leader, if you will, there are 5 choices to choose from. Now that person is sitting, so when we get to the second person, there are 4 people left to choose to sit down in that seat. With them both sitting, there are now 3 people left for the next seat, 2 people left for the next seat, and only 1 person left for the final seat. 5 times 4 times 3 times 2 times 1 is 120 ways these 5 people can sit in a row. A little preview of what to come. This counting down and multiplying 5 times 4 times 3 times 2 times 1 all the way to 1. That we could say is a factorial. Don't get too excited with that explanation point. That means factorial. 5 factorial means 5 times everything below it. 5 times 4 times 3 times 2 times 1 is 120. And your calculator can do factorials, and we'll look at those in another lesson. But just wanted to give you a preview of what's to come. Today what we're doing is just starting to counting with this idea of sets and what elements are part of the sets, using Venn diagrams to help us count how many people are in each group, and finally using the multiplication axiom to count different combinations and permutations of options that might be available. Tomorrow we'll take a look at some more types of counting, but for now take a look at the assignment and come to class with questions.